SwayamPrabha. Digital India. Educated India.
Welcome back. In lecture 32, we will cover multiple linear regression. The different concepts that we will cover is multiple linear regression, assumptions for multiple linear regression, and multiple linear regression using SPSS. So, when we talk about multiple linear regression, it's a statistical methodology for prediction of a continuous dependent variable from multiple predictor variables, which may be categorical or continuous in nature. So, for example, if y is equal to the response of the dependent variable and x1, x2 to xk are a set of explanatory variables, a simple linear regression equation would look like e to the power y equal to a plus b1 x1 if I take only one variable. But if I take multiple variables, then it will include a plus b1 x1 plus b2 x2 plus b3 x3 and so on. So, that should be a simple linear regression. So, it should be a multiple linear regression, and a simple linear regression, as you can see on in the slide, it is e to the when we are predicting for y, this is the response variable, we have only x1, a single variable, and a and b1 is the a is the intercept and b1 is the slope. So, over here if you see in this particular figure, where we have two variables, age and size. So, we are trying to predict one using another. In that case, this is the straight line that has been plotted, where size is equal to 0.83, which is basically A, and 0.96 is basically B. So, this into age. So, this 0.96 is the slope, which is the slope B1 is equal to rise by run. So, this is the rise and this is the run. So, if I can this gives us the intercept, this gives us the slope, and this value where this line matches, this gives us the intercept. So, this is the regression equation, basically means we are putting a straight line. The best way it goes through this particular data points that is there in this scatter plot. So, we have first done a scatter plot between size and age, and then trying to fit a line which best matches this particular this spread of plot, scatter plots or spread of these data points. Now, how do we do that? We do it by trying to minimize the sum of the square of residuals or errors or deviations. So, it is called either residuals or errors or deviation. Means what? That means for different values, we will have for prediction values of y, like y hat, we will have a difference with the actual value y I and I equal to 1 to n for each of these particular points, and then the one that minimizes this deviation, that means is basically it is a summation of all these deviations that is being added, and then the one value which actually minimizes this value, that actually is taken, and that actually gives us the result for this constant a and b1, this particular coefficients a and b1. So, this same concept is also used in multiple linear regression as well. So, out of infinite number of straight lines that could be drawn through a scatter plot between y and x1, the goal is to find the values of a intercept and b slope which best fits the data, and we will use that value, and we will find this particular equation, and we will see that when this minimizes, that actually gives us those values of a and b1. So, multiple regression equation, as I told you, is it's only we will add the number of x's, x1, x2, xk, and accordingly our beta coefficients or these coefficients will be also added, and so these are called partial regression coefficients. So, beta 1, b1, b2, bk are all called partial regression coefficients, and when x1, x2, xk everything is 0, then A is equal to Ey. That means the intercept in the last figure, when x is equal to 0, then we find that this is the value of y. So, that means this is the basic value that is there already. So, that is why this intercept is also here, and A equal this Ey equals the intercept when all the variables are 0. So, if we assume a linear, so there is a linear relationship between Ey and x1, while other explanatory variables are controlled. So, all these variables are linearly related when every other variables are fixed. So, there is also some assumption in linear. So, these are the different ways we these are the basics of a multiple linear regression, but in addition to this there are certain more assumptions that we need to be careful about when we do multiple linear regression. These assumptions are assumptions of linear relationship, assumptions of multivariate normality, no or little multicollinearity, no autocorrelation, and homoscedasticity. So, these are the different assumptions that we also need to check when we perform a multiple linear regression. And for in terms of sample size, at least some researchers suggest that at least there should be 20 cases per independent variable that we use. So, if we are using like 4 independent variables, so there has to be 80 samples that we need to have data for that, or in that scatter plot we need to have those 80 points based on which we can get the this partial regression coefficients for 4 variables and 1 intercept, for 4 coefficients and 1 intercept. So, let us talk about those assumptions. So, the first assumption is linear relationship. That means, relationship between the independent and dependent variables has to be linear. So, this could be easily checked if we do a scatter plot with individual variables, and we also need to be careful about the outliers. If there are outliers, we need to sometimes outliers change the final outcome or the regression line that we will actually decide, or the final line that will be fitted will be skewed because of the presence of outlier. That means, because it is far away or it is too away from the other group of data set, it will actually change the orient my fit line to a higher degree. So, that is why it is better to get rid of the outliers if it is of a certain value. For example, we can consider outliers we are lying beyond the standard deviation of 3, or it could be based on certain quartile. If we divide the data into different quartiles, in that way we can also decide certain data that we can get rid of beyond a certain value. So, we also test another assumption is multivariate normality, which basically means variables should be multivariate normal. That means it should follow normal distribution, and this could be easily tested by drawing a histogram of the data set. The histogram should look like a normal distribution. As we know, this is normal distribution, and histogram should, when we do the histogram, it should look like that. Or we can do a QQ plot, and in that QQ plot, if the points lie on a diagonal line, then the data is normal. Or we can do a PP plot, which is a probability plot. There also, if the data lies on the diagonal line, we can say that this is data is following multivariate normality. And we also have got goodness of fit test of normality, and in sometimes the data may not look like normal, but if I do a log transformation of that particular data, so it is the nonlinear transformation, then the data can become normal. So, that means even though the data does not appear to be normal, after a log transformation it could be turned into normal, and then we can use the log transformed variable into our regression equation. So, then we can also need to test for multicollinearity, and this means that when the independent variables are too highly correlated with one another. What it means is, when one variable changes, the other also changes. So, if both are, so we usually avoid taking both the variables in our regression equation. It is better to take only one of them. So how do, and so that means we need to check for multi-collinearity before we do our regression, and so that's why we need to do Pearson's bivariate correlation. We estimate this Pearson's bivariate correlation among all independent variables, and this could be checked. We can form a correlation matrix. We could list down all the variables in both x and y direction, and then we can have in both sides 1, 2. These are the variables 1, 2, 3, and then correlation between variable 1 and 2, 1 and 3. In that way, we can check. And similarly for 2 and 1, 2 to 3, and 2 to 4, and so on. So this is how we form a correlation matrix and check that. There is also another way to check this. We check the variance inflation factor, VIF. If the variation inflation factor is between 5 to 10, there is multi-collinearity, and when it is near 10, then it is very, very correlated, and we need to get rid of that particular variable. So we should remove independent variables with high VIF values. And in case of Pearson's bivariate correlation, different values have been suggested, like for moderate correlation, 0.3 is the value. When it is above 0.3, we call it moderate correlation. If it is above 0.5, we say very high correlation, and we should get rid of one of the variables. Now, we should also check for autocorrelation. Usually it is not a concern if the data is from a questionnaire survey, but if it is a time series data, it needs to be checked. And what it means is residuals should not the residuals will not be independent of each other. That is autocorrelation. And when values of y into x plus 1 is not independent from the value of yx, then we call it autocorrelation is there. And that needs to be checked, and usually we use the Darwin-Watson test to check this, and this Darwin-Watson test d values should be between 0 to 4, and values of 1.5 d values greater than 1.5 and lesser than 2.5 show that there is no autocorrelation in the data. If it is beyond that, then there is autocorrelation. So the total values that is possible, the range is 0 to 4. So finally we come to homoscedasticity. So that should be there in the data, because heteroscedasticity makes coefficient estimates less precise, thus increasing the likelihood that these are away from the correct population value. So if you see, this is heteroscedastic data. This is how the data would have been, we would have found the data, and this is homoscedasticity. We can see, observe over here. What we do is we plot the residuals. After our regression, we plot the residuals with the dependent variable, which is maybe total trips generated. We will show you in an example. We have done that. So this may be the one y. This is y. This is being predicted, and this is the residual of the predictions using the regression that we have, the regression equations that we have found. And once the residuals are plotted, this looks like this, which looks that the data is homoscedastic, whereas this data set looks it's a heteroscedastic, which is less precise, that is spread out, and that is where we need to be careful, and we may need to check the regression again. So multiple linear regression could be performed with many softwares. We can do it with SPSS software. We have already discussed the SPSS software. You can download that directly and apply this kind of models. And we have, I will show you an example. This is a data set of housing price in California. Each observation is a particular block group. So that means for each block is a zone basically. We take average values for different things, and each block groups around 600 to 3000 people. This data set is available in GitHub. So this is a free data set which you can also use, and the data types or the attributes that are being considered is housing median age, total number of rooms, total bedrooms, population in that particular block, total median income, median house value. These are average income, average house value, ocean proximity, how near is that particular block to ocean, and these are average age of buildings, rooms, and so on. So these are all continuous data. Only one data, that is ocean proximity, this is categorical. Ocean proximity basically means how near to the ocean. So 3 categorical variables has been used for that. So first what we need to do is to clean the data. That means even before we start the regression analysis, we need to check for outliers, and if there are a lot of outliers, we need to clean the data. And not only that, we also need to deal with the missing data. That means whenever surveys happen, some people may not fill the entire survey, or maybe some of the variables would be empty, some of the attributes would be empty. So, there are different ways we can take care of that. So, maybe 10% of the data set we can get rid of if this has got missing data, and but if you delete more than 10% of the data set, then we are actually losing data that we have spent money to collect. So, in that case, we can use other techniques where we can predict the missing values based on available complete observations. That means, we for that particular group of values, we can take an average of a similar kind of group, or we can take the average of the entire population, does not matter. So, we can use those kind of we can use the existing data set to replace this missing values as well. And then we can also be careful about the variable names. There are certain nomenclatures, certain rules that we follow, and like we do not have space between the variable names. We do not use special characters. We use this underscore character, and usually when we have a variable which has got many words in it, then we connect these words using this underscore character. And variables usually do not have letters at the beginning as well. So, then we come to dummy variables. We have discussed dummy variables earlier. So, these are basically categorical variables and cannot be directly used in regression. So, we need to convert them into dummy variables, like proximity to ocean. Sorry, I told you 3. There are around 1, 2, 3, 4, 5 categories of proximity to ocean. So, these are the categories. So, we could have 0, 1, 2, 3, 4. These are the different values. So, it could be in an island, it could be in a bay area, it could be in a near ocean, or it could be 1 hour from ocean, or it could be inland. So, this is how we can dummy code the data. So, the data where we can say that either it is this is the example data. The first one is island. So, it shows 1, and for everything else it is 0. For the next one, it is again island. So, it is 1 for the first category, and for everything else it is 0. For near ocean, so that is why this becomes this is the code. So, this becomes the last category, and the second category becomes 1, everything else 0, and so on. So, you can see that if I have got 1, 2, 3, 4, 5 categories, then we require only 4 actually dummy variables. So, we can ignore one of the dummy variables. This is just for explanation, we have used 4, but actually when we put them in the model, we will only take 4 of them, because if all of them are 0, obviously the final one would be 1. So, that is the idea that goes behind this, taking 4 instead of 5 variables. So, scatter plots, the next job would be to determine the scatter plots, which actually determines the pairwise relation between dependent variable and the various independent variable, and the scatter plots help us to visualize it. So, here we have done the scatter plots for the data, and we have done it based on total this side is total bedrooms and this side is median house value which is scaled. So, housing value versus total bedroom, housing value versus population, then and so on. So, these are the different scatter plots that we have done. So, we go to graphs in SPSS, we go to graphs, chart builder, then gallery, these are the menu options, subsequent menu option, then scatter or dot, and then drag and drop desired scatter plot type in the chart preview area, and drag, and then we have to determine which are the variables in x and y axis from the variables tab, and then putting OK, we can get this particular scatter plots. So, this is the correlation matrix that we need to generate. This is matrix of pairwise correlation of variables, only one side is done, and so we can see that it is this correlation shows the strength of relationship between variables. Two highly correlated variables should not be included in the regression model, that we have already discussed. So, because it results in inconsistency, and as we can see over here, there are certain variables which are very correlated. For example, total number of bedrooms is correlated with population, household, and total rooms. So, instead of taking this 4 variables in the equation, we can take only one of those in the equation, and that would be good enough. So, instead, we can replace population with total bedroom, we can replace households with total bedroom, or we can replace total rooms with total bedrooms, because these are correlated data. So, that means here the correlation values are shown over here. These are very high correlation values. So, we can that means with population it is 0.878, household 0.98, total rooms 0.93, and so we do not need to take all of them. Similarly, we have got high correlation between households and population as well, and again total rooms and households. So, that is why this actually helps us to decide which variables to include in the model, and a more efficient way to build a model. This is the PP plot that we talked about. So, this is used to check the closeness of the distribution to a given variable to the normal distribution. QQ plots also could have been done, and so we see that the more near to the data to this particular diagonal line, it is better. The more far away, it is a problem. So, this is what we need to check, and some of the variables which show skewness, like we discussed, we can take a natural logarithmic transformation of those particular variables, and then they may match this diagonal line. So, that is how we can also use variables which are not normal in our regression equation. So, the steps to perform linear regression in SPSS, first we go to the menu option, we click on analyze, then regression, then linear regression. These are the steps we need to choose. So, within analyze there is regression, and within regression there is linear option. And once we do that, and as we have discussed during the logistic regressions as well, we need to choose the dependent variable and the independent variables. We need to check that. Then the different model statistics we need to check on the boxes which shows the model fit and other estimates. And then there are several methods similar to logistic regression, like there is enter, stepwise, forward, backward. Enter basically means all variables are inside, but of course, we can set the confidence intervals that actually prevents some variables to be inside. Then stepwise basically starts with one variables and keep adding one more variable after one iteration if the results improve. Forward includes variables one at a time based on their explanatory power, and backward starts with all variables and removes one at a time based on the poorest explanatory power. And then finally, after the method we choose the appropriate method for our study, then we click on OK, and then we get the results of the linear regression. So, this is what we get. These are some of the results. So, the model in our model we are predicting the median house value using different independent variables. So, we are predicting housing price based on the different constituent characteristics of it. So, we start with 2 variables, independent variables. This is housing median age and median income of the people living there. So, we start with that. We also have a constant value. It is a default value of house price when all variables are 0. So, if x1 and so both these variables are made 0, then automatically this constant value will become the actual housing price. The model summary shows that the model fit, what percentage of variance is explained, and then adjusted R square is basically adjusted R square gives us R square, but it is penalized by the number of variables, or the more complex a model is, more it would be penalized. And so, that is how adjusted R square is better than R square. The coefficients for each variable is their regression weight, and their sign shows the direction. That means positive or negative actually determines what influence it has got on the dependent variable. That means, if independent variable is negative, that means when it increases, the dependent variable decreases, and vice versa. So, F test is also done, which actually shows the significance of the model structure. That means, if the inclusion of these variables is improving the amount of variance, is explaining a significant amount of variance. So, F value actually helps us to determine the overall integrity of that particular model. and its coefficient has got a significance value which is p value like earlier, and significance of 0.05 means 1 to 0.05 or 95% confidence interval. And as a rule of thumb, we consider a variable to be significant if the coefficient is significant at or less than 0.05. But we can also say that sometimes some variables are very important and they may not be significant at 95% confidence interval, but we can in that case reduce this value to 90% confidence interval, and that also could be chosen. Now, regression models are not sacrosanct. We can always change the structure of the regression model. For example, over here we have added some more variables. So, here we see that we in addition to median age and median income, we have added this categorical variable island, bay, near ocean and inland. So, these are the 4 categories that has been added. So, once we add this particular value, we see that R square value has increased from 0.510 to 0.597 as the number of variables. And this is one, and also these variables are significant. So, inclusion of the categorical variables is actually improving our model, and here we can improving this and here you see we have taken only 4 variables instead of 5, and the model could be interpreted as cost of house in a block increases with age of house and income of people in the block, because both are positively related. Additionally, house on island are most costly, followed by houses in bay area and near ocean. So, these are all positive indicators. If the house is located inland, the cost of the house decreases. That is because there is a negative sign to this particular variable. Then in model 3, we add another variable which is population. Population. So, we see that the overall R square does not change, and also we see that the coefficient value is, the significance is 0.908. So, it is not significant. So, we can drop this particular variable. So, as I was telling you earlier, sometimes even though a variable is not significant, of course, not to the level of 0.908, but if it was near to our around 90% confidence interval or maybe a little bit lesser as well, we can include a variable if it has got lot of theoretical importance. That means, from a priori knowledge, we know that this variable is very important, is a good predictor, and we, even though it is not within significant, we may include that because maybe in another data set, when we apply this regression, it would be very significant. So, that is how we develop a regression model, and as you have seen, we can have different versions of the same model. So, these are some of the references you can use. And finally, we can conclude by saying multiple linear regression is one of the most common statistical techniques to build predictive models. However, care should be taken that all assumptions are satisfied, because we have gone through many assumptions that needs to be taken care of, and inclusion of independent variables in a model is an iterative procedure along with testing of signs, that is the direction in which the positive or negative signs that gives the direction, and other model fit statistics for consistency. And variables which change signs in different iterations indicate correlation with other variables. That means, if I add another variable and we see that the sign has changed of one of the variables, that means this variable is correlated with another variable and we need to get rid of that or adopt any one of those 2 variables. So, that is how we do a multiple linear regression. Thank you.